In this video, we provide an introduction to molecular shape and geometry by discussing the fundamentals of VSEPR theory. All right, let's begin with the acronym. VSEPR means or stands for valence shell electron pair repulsion. Okay, and it's a very common and useful model to predict the geometries of very simple molecules from the Lewis dot structures. Okay, so in the determination of the shape, the starting point is the Lewis dot structures, so you need to know how to draw those structures for simple molecules, and then you can build concepts of VSEPR theory on top of Lewis dot structures to predict molecular shape. All right, so as the name indicates, okay, the central idea of VSEPR theory is that electron groups or electron pairs repel each other. And that is what dictates the geometry around a central atom in a molecule. All right, so to illustrate a little bit how those electron groups or electron pairs repel each other, I have here some props, which are balloons in air, which we're going to assume that are electron groups or electron pairs. Okay, so suppose that my finger here is a central atom, and then there's two groups or two pairs of electrons around the central atom. The question is, well, what is the location, or what is the direction, the geometry, the shape of those electron groups so that electron repulsion is minimized? And you can clearly see that if I draw my hand as the central atom, right, these electron pairs tend to be as far away as possible from each other. In this case, the geometry that favors or that minimizes repulsion is actually linear. Okay, if I try to generate a bend geometry, I have to add some energy, but I remove the energy, then those electron pairs recover that linear shape. Okay, so clearly the type of geometry that you will get is depending on the number of electron groups or electron pairs that you get. And then what we're actually going to do here is write a map of what the geometries that you get are for a given number of electron groups or electron pairs around a central atom in Lewis dot structure. Okay, so the first number in this column is going to be the number of pairs, which I prefer to call groups, as you will see in just a little bit. Okay, groups. And this is what we call the electron group arrangement, which is simply the geometry that those electron clouds have for the number of clouds. Okay, so when you have two electron groups or electron pairs, the electron group arrangement is what we call linear, and that is what you have seen before. All right, so in the following, we're going to try to look at what happens when you have 3, 4, 5, and 6. Okay. All right, so continuing with the props, I'm going to try to look at 3 groups of electrons. Okay, so same as before, my fingers here would represent the central atom, and then the balloons are the electron pairs or the electron groups. And you can see that when you arrange those electron groups as they want, right, this happens to be a trigonal planar shape, right? So you can see that the 3 groups of electrons are in the same plane, right? So in this case, it will be a plane perpendicular to your view, or in this case, sorry, a plane parallel to your view, or in this case, a plane perpendicular to your view. And the angles between them are about 120 degrees, right? So this is what we call trigonal planar. Okay, I could try to bend this to make it pyramidal. Okay, but to do that, I need to supply some energy. If I remove the energy, I recover immediately the trigonal planar shape. Okay, so for when you have 3 electron groups around a central atom, then the electron group arrangement is what we call trigonal planar. Great. All right, let's continue to try to build this with a 4th balloon. And when you incorporate here a 4th balloon, okay, now these things are getting very more difficult to do, because what I have here is a hand that is exerting a non-trivial amount of repulsion among these balloons. Right? Let's see if I can get this right. Right? The structure that you get that minimizes the repulsion between the electron pairs or the balloons. I'll finally get this right. will be something that we call a tetrahedron. All right, I think that probably is going to work out. Right, so notice that a tetrahedron is a shape that we can write as this. Okay, this is your central atom, and this will be those electron pairs, right? Okay, notice that you have that this pair, the central atom and this pair, are in the plane of the whiteboard, so that would be this balloon, my hand, and that balloon. And then you have a balloon coming towards you, and that is what this wedge means. And then a balloon going away from you, and that is what this dashed line means. Okay, this angle is 109.5 degrees. Okay, so this is the shape, the geometry that minimizes repulsion. There's other possibilities. For example, I can actually jam this into place, okay, by adding quite a bit of energy. And I could in principle get these four in the same plane. That is what we call a square planar, but clearly if I let this move, that immediately goes to tetrahedral shape. Okay, so for 4 electron groups, what we actually have is that the preferred shape is what we call tetrahedral. All right, so once you have 5 and 6 electron groups, it's very difficult to use the balloons as a prop. Instead, what we're going to do is here draw how those shapes look like, and then explain a little bit about them, right? So when you have 5, the shape that you get is called trigonal bipyramidal. And then what you have is that if we draw here atoms, okay, you will have 2 atoms linear to each other. So the angle here will be 180 degrees. And then you will have here a second set of atoms, which we're going to call E. Okay, E and E. And these 4 atoms, E, X, E, E, would be in a plane perpendicular to these 2. Okay, and they would be in a trigonal planar geometry in that plane, right? So the angle between these E, X, and XE, that will be 120 degrees, 120 degrees, 120 degrees, and again, this is in a perpendicular plane to these 2 XA bonds. Okay, so that means that the angle between any one of AX, XE bonds, that is always 90 degrees. Okay, so that is 90 degrees, but it's also 90 degrees with respect to this one, and so forth. Okay, but within the plane, within this perpendicular plane where the 3 E atoms are, the angles E, X, E, those are 120 degrees. Okay, so this is the shape. This is the shape that minimizes electron repulsion, and that is what we call trigonal bipyramidal electron group arrangement. Right, so that is going to be trigonal bipyramid. Okay, and the last one is a little simpler when you have 6 atoms around, or 6 electron groups around a central atom. Okay, so you have 1, 2, 3, 4, 5, and 6, right? So the electron groups will be these bonds. Okay, the shape that you get out of this is something that we call an octahedron. Okay, so an octahedron is a well-known geometrical picture, right, where you have that the angles between all of the bonds here are going to be 90 degrees regardless of what plane you are. You always have 90 degrees, okay, unless it's in the opposite edges of the solid where you have 180 degrees. Okay, so that is what we call an octahedron, and that means that the electron group arrangement here is octahedral. All right, so we stop at 6 because it's very rare to find molecules that have more than 6 groups of electrons around a central atom. Okay, there's a few examples, but there are not very many for an elementary or fundamental understanding of molecular shape. We actually don't have to go beyond 6. And again, that's what we call the electron group arrangement. Now, the final question that we want to talk about in this video is how do you determine the numbers of electron groups from a given Lewis dot structure. Okay, so let's take here a couple of examples. Okay, so for example in water, if we draw the Lewis dot structure for water, what you will get is a Lewis dot structure that is like this. Okay, so the number of electron groups is going to be 4, because you have that's one electron group, that is one electron group, that's a different electron group, and that is a different electron group, right? So you have that each of the lone pairs of electrons contribute as a single group, and each of the single bonds that you have here, they contribute also as one electron group, right? So the number of electron groups that you have here would be 4, and that means that the geometry of those electron groups around the central atom is what we call tetrahedral. Okay? Let's do a different example. And this is going to be a made-up molecule. It's going to be X, A, and then this. Right, so we have here a Lewis dot structure for a molecule, where if we put here 3 lone pairs, every atom of that molecule will see an octet, so that will be a good Lewis dot structure. Okay? Or perhaps we can replace this by B to make this a little bit more clear. Okay? All right, so the important thing is that we center on the central atom and then try to determine the number of electron groups that we have here. All right, so there will be one electron group, there is another electron group, and then we have to think about this double bond. Okay? If you're thinking about pairs of electrons, you will be misled, because that would make you assume that you have here one pair of electrons and then another pair of electrons, and that would give you a total of 4 pairs of electrons around the central atom. Okay, that is not true for what we're trying to do here. This counts as just one single electron group. Okay, so a multiple bond, that means a double or a triple bond, they only count as one electron group, and the reason for that is that they are always in the same direction of space. Okay, they are aligned along the same direction of space, right? So they only count as one. For this molecule, then, you would actually have 1, 2, 3 electron groups. Okay, and that's why I prefer the nomenclature groups better than pairs. Okay, 3 electron groups, and again, the geometry of those 3 electron groups around the central atom X will be trigonal planar. Okay, so in this video we have introduced the concept behind VSEPR theory, and we have been able to map the number of electron groups with what we call the electron group arrangement. Now in the next video we're going to see how this electron group arrangement leads to molecular shapes, where we actually are going to have to think how many of those electron groups are lone pairs versus how many of them are bonds.